In this video, we will practice solving optimization problems, including minimizing the distance between a point and a curve. If you appreciate the content, please give it a like. Number 12. Find the length and width of a rectangle that has an area of A square meters and a minimum perimeter. We're going to treat this capital A like it's a number. Most optimization problems involve a primary equation and a secondary equation. The primary equation is an equation for the quantity you are trying to maximize or minimize. In this case, we want a minimum perimeter. So the primary equation will be a formula for the perimeter of this rectangle. Let's define some new variables to represent the length and width of the rectangle. You can either define them by drawing them into a picture like this, or you can say it in words like, let x equal the length of the rectangle and let y equal the width of the rectangle. But you have to define your variables using one of those two methods. So, using these variables, we can now write a formula for the perimeter, which is the sum of all the sides. So that will be 2x plus 2y. Notice that you had to invent this third letter, P, for perimeter. You really could have picked anything. You could have put a Q here if you wanted to. But that's something I need you to get used to. For an optimization problem, you're going to make up a letter to define your primary equation. The secondary equation will come from the fact that the area is A. And again, treat this A like a number, like it was a 25. So we know the area of a rectangle is base times height. So x times y must equal A. The primary equation must be written in terms of a single variable. That's where the secondary equation comes in. Let's solve this equation for y. So y is equal to A over x. Now we can substitute this expression in for y in the primary equation. So we have P is equal to 2x plus 2 times A over x. Remember, we are treating A as a constant, so really P is now a function of one variable, which is x. Ultimately, we need to find P prime and make a P prime sign chart. But I'm going to rewrite this a tiny bit. P is equal to 2x plus 2a, and I'm going to take this x out of the denominator and write it as x to the negative 1 power. I think we can find P prime pretty easily now. The derivative of 2x is 2, and the derivative of 2ax to the negative 1 power. Using the power rule, we're going to bring this negative 1 to the front, so we will have negative 2a x to the, and we reduce the exponent by 1, so that's the negative 2 power. In order to make the P prime sign chart, it will be easier if we rewrite this as a big old fraction. I am taking x to the negative 2 power and dropping that back down to the denominator. I need like terms here, so I see I've got x squared in the denominator, so I'm going to multiply the 2 by x squared over x squared. So really on my next step, I will have 2x squared over x squared. Now I can combine these into a single fraction. P prime equals. So you see it's going to be 2x squared minus 2a. I think I will factor out that 2 while I'm at it. So 2 times x squared minus a over x squared. That's a nice P prime. In order to make the P prime sign chart, we need to find the values of x that cause P prime to equal 0 and make P prime undefined. So a rational expression, a fraction, will equal 0 when the numerator is equal to 0. And the 2 can't be 0. So I'm going to skip to x squared minus a is equal to 0. Adding a to both sides, we get x squared is equal to a. Taking the square root of both sides, x is equal to the square root of a. We will not do the plus or minus because x represents a length which cannot be negative. A rational expression is undefined when the denominator is equal to 0, which means x equals 0. Well, I'm throwing this out. X can't be 0 or we wouldn't have a rectangle. Set up your p' sign chart using your one critical value. Include 0 as the lower limit of the domain. This is a domain limitation suggested by the context of the problem. Be sure to label the sign chart as p' and make a row for each factor. It's actually up to you exactly how many rows you want to make, but I like to make as many rows as possible so that each row is very simple to evaluate. Now let's decide whether these factors are positive or negative in each one of the two intervals. Well, 2 is always positive. And x squared minus a is equal to 0 right here at the square root of a. So this is where it might change signs. So we really have to use a test value. Let's plug in 0 as a test value. Then that would leave negative a. So the values are negative to the left of the square root of a and positive to the right. If we plug in something bigger than the square root of a, so say if we plugged in 2 times the square root of a squared, and then that would be minus a, then this would be 4a minus a, that would be 3a, which would be positive. We probably didn't need to overthink it like that. Squaring something, it's never going to be negative, so this is going to be positive in every interval. So the overall sign of p' will be negative in the first interval and positive in the second interval. The first derivative test tells us that p has a relative minimum at x equals radical a because p' changes from negative to positive. Unfortunately, for an optimization problem, relative minimum is not good enough. We need to know that the perimeter has its absolute minimum at x equals radical a. Luckily, this is a special case. When you only have one critical value on the entire domain, you can actually use a sign chart like this to determine that p has an absolute minimum. The one critical value of radical a separates the domain into two intervals. Because p' is negative for the first part of the domain and then positive for the rest of the domain, the perimeter is decreasing on the first part of the domain and then increasing for the rest of the domain. Therefore, the value of the perimeter at radical a must be the absolute minimum. This is the entire domain. Nothing else happens. Here's how you word that. Instead of saying p' changes from negative to positive, we say p has an absolute minimum at x equals radical a because p' is negative on the interval from 0 to radical a, and p' is positive on the interval from radical a to infinity. Again, that covers the entire domain. That's how we know this is the absolute minimum. We need to find the length and width of the rectangle, so we need y as well as x. So we say at x equals radical a, and then now we plug that in for x. So y is equal to a over radical a. There's nothing wrong with this, but if you rationalize this fraction, it will simplify. If you multiply by radical a over radical a, you get a radical a over a, and then the a's cancel out, and you are left with simply radical a. So the value of x and y are actually the same. Make sure you answer the actual question with a closing sentence. The length and width that minimize the perimeter are radical a and radical a. For the last three problems, we need to find the point on the graph of a function that is closest to a given point. This first one is calculator active. Before we go to the calculator, you know that y equals x squared is a parabola like this with a vertex at 0, 0. X minus 1 squared is that same parabola shifted 1 unit to the right. It's always the opposite of the way it looks. The point -5, 3 is over here somewhere. We are trying to find the point on the curve that is closest to the point -5, 3. For now, we have to call it x, y. So there is a distance here that we can call d that we need to minimize. Here's the formula for the distance between 2 points that you learned back in geometry or algebra 1. So this is the formula for the distance between these 2 points. This is the quantity we must minimize. Before we can do that, we need to rewrite the distance formula in terms of a single variable. That's where this secondary equation comes in, the equation of the curve itself. Think of this as y equals x minus 1 squared. We can substitute x minus 1 squared in for y right here. So here's the distance formula written in terms of a single variable. Normally we would go ahead and find d prime so that we can make a d prime sign chart. But because of the square root, taking the derivative of this would be very ugly. So there's a shortcut that we can use for these distance formula problems when this radical is involved. We can define a new letter that equals the inside part of this expression. I'm calling it I for inside. If we can find the value of x that minimizes I, that same value of x will automatically minimize the whole expression d. It's a little easier to find I prime than it would have been to find d prime. So let's do it. So first we take the derivative of the outer function, so the 2 goes like that, and then we have the x plus 5 on the inside. Normally we would multiply by the derivative of the inner function, but that would just be 1, so we don't need to do that right now. Moving on to the second term, the derivative of this outer function is going to put the 2 out here like this. And for the moment, let us leave the inner function alone. So we have x minus 1 squared minus 3. But then we must multiply by the derivative of the inner function. So the derivative of this is going to be 2 times x minus 1. The derivative of minus 3 is 0, so that's the end. I am going to simplify this a tiny bit because, 2 times 2 is 4. So this is our expression for I prime. I can see why this problem is calculator active, because now it's time to make an I prime sign chart, which means if we were doing this by hand, we would have to somehow set this equal to 0 and solve, and that would be very difficult. However, any graph is a sign chart. So if I want an I prime sign chart, I can just type the equation for I prime into my calculator or Desmos, and then that graph itself becomes a sign chart. We can easily see where I prime is positive and negative. I'm going to type I prime here on y2. I always put derivatives on y2 for some reason. It's about to go off the screen, so you're going to see me type in this last part. Times x minus 1. So I have I prime typed in as y2. Let's take a look at the graph and see what we can see. Okay. I prime is equal to 0 at this one critical value, something close to -1. We'll find it in a second. But I prime is negative to the left and positive to the right. This intersection point appears to be at -1, but let's be sure. I like to find zeros by graphing the x-axis itself. So I'm going to go back to my y equals, and I'm going to put an equation y equals 0. So now I can just find the intersection point by hitting second, trace, and then option 5 for intersect, and I can move the pointer close by, and hit enter 3 times. Enter, enter, enter. Oh look, it really is -1. Before I show you how to write up the justification, remember we are trying to minimize the distance d, but right now we are minimizing I. So you have to compensate for that with this one tiny phrase. We are going to say I, thus d, has an absolute minimum at x equals -1 because I prime is negative from -infinity to -1, and I prime is positive from -1 to infinity. Be sure not to say anything about I prime changing from negative to positive. That's your first derivative test, which only tells you that I has a relative minimum at x equals -1, not an absolute minimum. Since I only has one critical value of -1, it separates the entire domain into 2 intervals. And because I prime is negative for the first part of the domain and then positive for the rest of the domain, that means the actual value of I must be decreasing for the first part of the domain and then increasing for the rest of the domain. Thus, I has an absolute minimum at x equals -1. This is the entire domain. Nothing else happens. We need to find the point that is closest to the curve. That's x and y. So far we found that x is -1. So we need to find the y value that goes with it. We're going to find it by plugging -1 in for x. So at x equals -1, y will equal -1 minus 1 squared. That's -2 squared, which is 4. So we have the point -1, 4. Don't forget to answer the actual question with a closing sentence. We were supposed to find the point on the curve closest to the point -5, 3. The point on the curve closest to -5, 3 is -1, 4. Let me add one small but important detail. Somewhere in your work, you must explicitly state that I prime equals 0 at x equals -1. Always list your critical values. Notice that number 15 is not calculator active. We need to find the point on the curve y equals the square root of x that is closest to 4, 0. We need to find the point on the curve that minimizes this distance. Let's call it d. According to the distance formula, the distance between these 2 points is equal to this expression. We need to write this distance in terms of a single variable. So let's use the fact that y is equal to the square root of x to substitute radical x for y. And I'm not going to write the 0. You were probably taught that when you square a radical, the radical goes away and it's just going to be x. But technically, this is equal to the absolute value of x. Sometimes this matters. Not this time because we are in the first quadrant where x was going to be positive anyway. So we can go ahead and simply write x, but I just thought I'd mention that. So here we have written the distance in terms of a single variable. This is the quantity we need to minimize. We can use the shortcut. This is another one of these square root problems. So let's define I as the inside part of this expression. If we can find the value of x that minimizes I, that same value of x will minimize the distance. So we need to find I prime and make an I prime sign chart. Taking the derivative of the outer function gives us this. The derivative of the inner function would be 1, which we don't need to write. And the derivative of x is 1. So this is I prime. Distributing the two, I prime equals 2x minus 8 plus 1, and negative 8 plus 1 is negative 7. So I prime is equal to 2x minus 7. We need to find where I prime is equal to 0 in order to make the sign chart. And let's do that in our heads. X equals 7 over 2. One critical value. Set up your sign chart like this. 2x minus 7, and thus I prime, will be negative for values of x to the left of 7 over 2 and positive to the right. For the justification, we say I, thus d, has an absolute minimum at x equals 7 over 2 because I prime is negative from negative infinity to 7 over 2 and positive from 7 over 2 to infinity. Do not say anything about I prime changing from negative to positive. That only gives you a relative minimum, not an absolute. And be sure to say thus d, because this only gives us the absolute minimum of I, but we really need to minimize the distance d. We found the value of x, but we also need the value of y, which is just the square root of x. So when we write our final answer as a sentence, y will equal the square root of 7 over 2. Don't forget to answer the actual question with a closing sentence. The point on the curve closest to the point 4, 0 is 7 over 2, radical 7 over 2. For number 16, we need to find the point on the curve y equals the square root of x minus 8 that is closest to 12, 0. Pause the video and try to do this one by yourself. The graph of y equals radical x looks like this, and the graph of y equals the square root of x minus 8 will be shifted 8 units to the right like this. We need to find the point on the curve closest to the point 12, 0. In other words, we need to minimize this distance d. I keep drawing these pictures as a way of defining my variables. If you don't feel like drawing these pictures, then you have to write out more words and define your variables by saying things like d equals the distance between the point x, y and 12, 0. But I find it easiest just to draw a picture and include all of your variables in the picture. Now that we shifted over, I should write y is equal to the square root of x minus 8. Using the distance formula, this expression gives the distance between these 2 points. However, we need to rewrite this formula in terms of a single variable. So let's use the fact that y is equal to the square root of x minus 8 to make a substitution right here. Quick side lesson about squaring a square root. The radical and the exponent sort of cancel each other out, but the result is technically not x minus 8, but rather the absolute value of x minus 8, because this expression will always be positive. It can never be negative. However, we're going to gloss over that because we are in the first quadrant, so it was going to be positive anyway, so the absolute value won't really matter, and we can just put x minus 8 right here. Sometimes it does matter, so be aware that when you square a radical, it's really the absolute value of whatever was in the radical. To make it easier to differentiate, let's use the shortcut where we let I equal the inside part of this expression, x minus 12 squared plus x minus 8. Now we can find I prime very easily. And again, if we find the value of x that minimizes I, that same value of x will automatically minimize d. So I prime will be 2 times x minus 12. The derivative of the inner function is 1, so don't worry about that chain rule. The derivative of x is 1, and the derivative of negative 8 is 0. So this is I prime. To make the I prime sign chart later, we need to find where I prime is equal to 0. Subtracting 1 from both sides, we get 2 times x minus 12 is equal to negative 1. I think I'm going to just distribute this 2 right now. So we have 2x minus 24 is equal to negative 1. Adding 24 to both sides, we have 2x is equal to 23. And dividing both sides by 2, we get x is equal to 23 over 2. One critical value. Okay, I probably should have done this in the first place, but I'm going to simplify I prime before I write it up into my sign chart. So this was 2x minus 24 plus 1. So I prime is equal to 2x minus 23. So set up your I prime sign chart like this. 2x minus 23. Make sure you label it as I prime, and there's our one critical value. So we need to decide whether this factor is positive or negative in each interval. It's pretty easy to tell that it will be negative to the left and positive to the right. I think we have a domain limitation we have to deal with. The square root does not go past the 8. So we are talking about values of x that are strictly bigger than 8. So let's put that on the sign chart right here. Okay, so because we have one critical value, it is separating the domain into two intervals from 8 to 23 over 2 and then 23 over 2 to infinity. Because I prime is negative in the first part of the domain and then positive for the rest of the domain, we can be certain that I itself is decreasing for the first part of the domain and then increasing for the rest of the domain. Thus, an absolute minimum at 23 over 2 as opposed to merely a relative minimum. Don't forget to connect this back to the original distance d that we are trying to minimize by saying I, thus d, has an absolute minimum at x equals 23 over 2 because I prime is negative on the interval from 8 to 23 over 2 and positive on the interval from 23 over 2 to infinity. Be careful not to accidentally say because I prime changes from negative to positive. That's your first derivative test and only gives you a relative minimum, not the absolute minimum that we need. This trick of saying absolute minimum this way only works when you have a single critical value on the entire domain. Don't forget to plug 23 over 2 in for x to find y. If this was a test, I would leave my expression for y like this. No need to waste time simplifying. However, 8 can be written as 16 over 2, and 23 minus 16 is 7. So y equals the square root of 7 over 2. Don't forget to answer the actual question with your closing statement. We were supposed to find the point on the curve closest to the point 12, 0. The point on the curve closest to 12, 0 is 23 over 2, radical 7 over 2. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.